Thanks again. This will be a little bit different because it will be a little bit less visualization, a little bit more generic analysis, which could be visual, but could be other things as well. It will be large scale. We will care about strong scalability, not just weak scaling. We'll cover examples that are non-trivial to parallelize, that have real communication overheads. And we'll discuss ways that you can basically parallelize your own customized data analysis, therefore the name DIY, do-it-yourself data analysis. Not to be confused with DIY home repair, which is the way my wife and I tend to spend weekends, but that's a different story. Target architectures here are HPC, largest supercomputers. Of course, the same techniques can apply to smaller clusters, desktops and laptops, but they really shine on the largest machines. And in general, we'll be talking about trying to push analysis closer to the source, closer to where data are computed or generated. The buzzword for this is in situ data analysis, and we'll describe kind of how that's done as well. By the way, feel free to interrupt me with questions whenever they come up. First, a little bit of background. So if this is a supercomputing facility, right, you have compute nodes and some parallel file system and some attached analysis cluster like Mira and Tukey. In the old days, the mode was, well, basically simulations would dump everything to storage, and then later offline in post-processing, you would read all of that back and do some kind of visualization or analysis. The size of the arrows here denote the amount of data movement that that would require. And the newer approach is to try to push some of that analysis early while data are being computed, right on the big machine at the same time, and therefore have less data, skinnier arrows to save and to further post-process later on. Okay, so that's sort of the landscape that we're working in. And when we say data analysis here, I'm using a very loose definition. I basically mean anything that is done to the raw data beyond its initial generation. So if you're a cosmology simulation like HACK, for example, your job is to run a nonlinear set of partial differential equations and to produce raw particle data. But that's not the end of the story, because in order to derive any kind of meaning from that data, much more follow-on analysis has to happen, but it's kind of outside the scope of what that simulation does, right? So any of those steps, to me, are analysis. They could be as simple as transforming the data from particles to a mesh. They could be taking that mesh and further deriving regular grid density fields. They could be deriving statistics, 2D, 3D plots, visualizations, the kinds of things that you've been hearing about this afternoon. All of that is fair game. In general, analysis is some kind of a data flow, a DAG, like in the upper right. And any one of those round nodes that somehow transforms data, to me, is an analysis step. And we're interested in taking one of those nodes, something that would make sense to do probably at the left side of that graph, closer to the source, and write your own analysis in a way that it could be scaled up and run on large HPC machines. Because if it's going to run in situ with the simulation, then it better be able to run on the same machine. It better be able to scale the same number of processes as that simulation, so hundreds of thousands of processes. And it better do that well so that it doesn't use all those resources, right? Because those resources are valuable and they're needed for the simulation as well, right? So that's sort of that's the goal here, okay? And examples of these that are sort of like our success stories for DIY are shown here in one slide. We could We have individual results from each of these. All of these, with the exception of one that's being written right now, have been published previously in supercomputing, IPDPS, various other high-impact venues. But with the time that we have today, we're just going to sort of put them up there and say, these are all the things that we've been able to do. Some are in the field of CFD, so parallel particle advection to compute streamlines and path lines. Triangulation of those into surfaces in parallel is another challenging analysis problem. Again, these are not trivially parallelizable. These require intense communication to pull off. Extracting structures from flow fields, divergent and coherent Lagrangian structures by a technique called finite time Lyapunov exponents, FTLEs. In a totally different vein, taking a data set and computing its information content. This is Shannon's entropy, the same entropy that you would compute for compression or for communication. We have done that in parallel as well. Most recently, we've switched from simulations to experimental data. This is light source data from a synchrotron light source, the APS at Argonne, and it's reconstructing in parallel images, retrieving the phase basically from complex operation of the detector, collecting images from samples that are hit by high energy X-ray beams, doing that in parallel. The more Smale complex in the lower left is a topological structure, again, something completely different. That is extracting a graph from a data set, and that graph is segmented according to the gradient behavior, uniform gradient behavior of the underlying data. Also things that are purely geometrical, like tessellating a particle data set and computing a Voronoi and Delaunay tessellation. We'll return to that example towards the end of the talk. Okay. What do all these have in common? Well, first of all, they're from science problems, right? So we're not really interested in the DOE space, at least, in web or enterprise or social networking or like that. These are spatiotemporal science domain problems, the kinds that you've been studying in the last week. They tend to be big, right? We work in big resources, big science, big data, big architectures. Most of the algorithms for doing those analyses are typically serial, or if they are parallel, they don't parallelize very well. And we want to solve that problem. We want to take something maybe that is just a serial kernel, and we want to parallelize that out. That's what we're trying to do. Okay. Ways that we go about that, we've hinted at some of these already, right? Processing data closer to the source, in situ analysis. Being able to write scalable analysis algorithms and an infrastructure for writing those is what this talk is about. Parallelizing in different programming models, coarse grain, MPI, process parallelism combined with fine grain, OpenMP, whatever, thread parallelism. Writing an infrastructure that is reusable, right? A library that we can call over and over again. And basically kind of this DIY idea of developing this into a library that is an API where users write their own main programs for their analysis. So not a GUI interactive tool, but think now more like VTK, an API where you write a main program yourself. Okay? And thinking about this a little bit ahead of time helps. So forming an abstraction for how we're going to pose a parallel analysis problem is a good thing to do in our experience. And rather than just diving in, and the way we started, which was just dive in and write a bunch of MPI and inject it into our code, and in a year you've got something done, but it's not reusable, it's not really well thought out, it's not modular, right? Taking a step back, and now after a few years of doing that and thinking about this more systematically, we realized that one key abstraction is that of blocks as opposed to tasks. So you've been studying MPI, OpenMP, and all this time you've been learning about how tasks communicate with each other, right? MPI rank 0 sends a message to MPI rank 1, right? I'm saying, throw all that away, and let's rethink that as block 0 sends a message to block 1. Now, what are blocks? Blocks are subdomains of the problem. So it's a data parallel decomposition of the problem. We've seen that. That should not be anything new. But the idea that these blocks are first-class citizens, pieces of the data, are first-class citizens that do work on themselves and communicate with each other rather than cores or processes or threads. Communicating with each other is a new concept for many of us. Okay? Now, what does that buy us, having this abstraction, right? Well, it buys us that these blocks can now be assigned flexibly to tasks. Blocks can be different sizes. The same program, literally the same program, can one day, or even during the course of the same run, have blocks that are at one point one size, another point the configuration changes and they are smaller or more numerous. Those blocks may be located in flexible ways. At one point they may be assigned one way to tasks or processes. At another point they can be assigned differently. They can be overloaded. Multiple tasks can have duplicate copies of the same block. Even in HPC machines with different levels in the memory and storage hierarchy, at some point that block may be in core, in memory. Another time that block may be sitting on storage. And still, block 0 can communicate with block 1. Maybe not immediately. Maybe that communication has to be enqueued. And later, when that block is in core, that messaging can actually happen. But all of this is possible basically with the same code if we just kind of think about blocks instead of tasks as the units of decomposition, right? So that's one important thing, and I can't stress that enough. That's sort of the whole, well, one of the keys to making this work, because it enables a whole kind of a lot more powerful approach than if we think about tasks like we usually do. Okay, so that's the first lesson here. The second lesson is just kind of software encapsulation. So in the old days when I started doing this, to write a parallel analysis algorithm, well, we'd write a parallel algorithm, and into it we'd inject a bunch of parallel commands. MPI, OpenMP, pick your favorite programming model, right? This is what you would do, right? Again, taking a step back and kind of organizing ourselves a little bit, it makes much more sense to have kind of this interface between a serial analysis algorithm and a reusable library of data movement operations, basically algorithms like a global merge reduction. This is an algorithm that you would write in MPI, and it's, to make it generic and flexible, it's fairly involved. But if you do that once and encapsulate that in a library that then you could call through an interface, through an API, right? Then all of a sudden you can reuse it, you can improve it, you can, separate it from the rest of the code, you can benchmark it, you can categorize your approaches by saying, oh, this parallel algorithm is a merge reduction. This one is a swap reduction. This one is a combination of a nearest neighbor followed by a merge reduction, right? We can organize our thinking. Analysis algorithms don't have to be like the Wild West anymore, okay? All of these things are what I'm advocating by kind of separating out the data-intensive parts of the analysis from the custom serial operation that basically you have to provide, because this is generic, right? This doesn't know anything about Morse-Smale complexes, about particle advection, about Voronoi tessellations, right? This knows about decomposition into blocks and communication between blocks. And that's what DIY is. And no DIY talk would be complete without the one highlight slide of the library and why it's so good. But I want to stress here that this talk is more about the concepts that underlie this particular implementation than it is about this particular implementation. But there does exist a DIY library. It's fairly small. You can link it statically to all of your codes because it doesn't really take up any space. It's easy for us to maintain it. It builds easily in autoconf, /configure, and make. is basically all you have to do to install it. And it provides modules for parallel I/O, for block decomposition, for communication between blocks, and a couple of other loose utilities. And the way it's used in a software stack is it sits on top of a parallel programming model like MPI, and below some specific analysis library like information theory library, like a particle advection, even like VTK, for example, or a geometry library, because these are the things that do the specific analysis. This is the infrastructure, kind of the base layer for the data movement. Okay? And then on top of that can sit simulation codes or visualization tools, kind that you've been seeing today. All right? So that's kind of where we sit. And in a longer talk, I would speak individually about each of these 9 topics. In a short talk like today, we'll just have a quick overview of sort of the fundamentals of what a library like this ought to provide. First of all, there's this separation, this interface between the high-level analysis and the common data operations that are reused over and over again. Data are decomposed into blocks. Blocks are assigned flexibly to processes, right, and reassigned and reconfigured. Furthermore, they're grouped into neighborhoods, right? This is just another way to further decompose and combine blocks into kind of smaller or larger units that are still scalable. Here are some examples of neighborhoods in a regular grid, neighborhoods in an unstructured grid. Neighborhoods can be 4D because, in general, we have to handle time natively. All science data sets are time varying. We can have multiple instantiations of blocks and neighborhoods of blocks. We have high-powered communication algorithms that communicate between blocks, right, not between processes. We have some I/O utilities. And finally, we need to integrate with other parts of a scientist's tool chain. We don't intend to replace everything that you do with DIY. We tend to add to it by providing these capabilities whenever they're convenient for you. For example, that means you don't have to use DIY's parallel I/O. You can use HDF5, NetCDF, Adios. You'll learn about these things tomorrow, I think, but if you haven't heard of them before. So it's important to play well with the rest of the ecosystem, not to try to replace all of it. Okay? That also means that you can call MPI and OpenMP yourself. We're not trying to wrap all of that from you. We're not trying to hide it from you. We're just trying to provide some utilities that help you to achieve results that you need. Okay? And in terms of usage, I'm going to give you a kind of a high-level overview of how you write a DIY program. And I'll give you a few of these flow charts of kind of example templates of that. I probably will not go in great detail through them so that we stay on time. But first of all, there's a DIY repository. I'll give you the URL. It's a Git repository. It's public. It's in the last slide. But in that repository, you'll see a README. You'll see a user's manual. And you'll see lots of examples of these types of programs, small toy programs that you can look at and play with. But generally, and I should say these are C or C++ programs. The API is C compatible. DIY itself is written in C++, but its API doesn't expose any C++ constructs. It's all C, so kind of lowest common denominator for C and C++. And you will basically call on DIY to decompose your domain for you, or you can provide an explicit decomposition that you already have existing. DIY can read data in parallel for you, or it may already be in memory if it's an in situ analysis. You will write your own local serial analysis, or you will provide one that may be written already. So for the computational geometry, other applications, there are good, mature tools that just happen to be serial, and you can just use them. You don't have to start this step from scratch necessarily. DIY gives you 3 main flavors of communication algorithms. And you can call those as many times as you want, and you can mix and match every time you go through this loop. And then eventually you're going to write out some results probably to storage, and you're going to end, right? That's sort of typical. The point here is that you're writing a regular program in a high-level programming language, and DIY is an API. So you can call these things however you want. You can write whatever control flow you want here because you're in a regular programming language to do this. Okay? Now, I have a few examples. That's sort of the generic template of what every DIY program looks like. And then I have some specific examples of what these templates look like when you're doing this in the same core, when you're doing this in a separate core. We have multi-core machines, after all, today, so it's not unusual to think about running the simulation in one core for one time step and then copying the data over and running the analysis on a separate core while the simulation continues on the next time step in the first core. So that's what this diagram on the right is about. But in general, the same core is sort of the same flow chart that you've seen before. The one on the right just takes the analysis and pushes it off to a second core. There's an example of this in the repository, by the way. If it's a static analysis, so just one time step, we call this loop over the analysis and communication we usually call rounds. If there's multiple time steps, there's an outer loop for each time block. Time block can be one time step or several time steps, just a partitioning of the total time. So that is how we realize time-varying analyses. And for the communication algorithms, they kind of break up into two groups. The merge and the swap are global reductions on the left. And the neighborhood exchange, it operates a little bit differently, so that's on the right. And I probably don't have time to talk about these very much today. We'll have to, I think, take that offline. They program just slightly differently because they're fundamentally different patterns, different communication patterns. You can almost think of these as design patterns for communication that you reuse over and over again. God bless you. And what I wanted to do to close out is talk about one example in a little greater detail. And this is the parallel Voronoi and Delaunay tessellation. This is the most recent thing I've been working on, so it's freshest in my mind. I should also point out that in the 6 or 7 examples I showed you in the beginning, this being one of them, none of these things are done in isolation. These are collaborations with other university and DOE partners that I haven't listed there, but I can't take credit for all these things ourselves. Typically, our partners have the serial algorithm, and we tend to help them parallelize it. So more Smale complex is led by University of Utah, by the Ski Institute. Particle advection tends to be led by Ohio State University. Parallel tessellation is a collaboration between we at Argonne and Lawrence Berkeley National Lab. So I don't want to give you the wrong impression, like this isn't all just my work. These are various teams of people working together on each of these projects. So tessellation in particular takes individual particles. So think like molecular dynamics, cosmology, LIDAR, point clouds, anything that is a discrete set of particles, and it creates a mesh out of those particles. Okay? That mesh either has particles, one particle in the interior of each polyhedron. That's a polyhedral mesh called a Voronoi tessellation. Or the dual of that is one particle at each corner, at each vertex of a tetrahedron, and that's called a Delaunay tessellation. Okay, so the idea is we're making a continuous field out of what used to be a discrete set of particles. And we're trying to do that in parallel at large scale. Again, not a trivially parallelizable task. Something also that hasn't been done before or was done back in the 90s at scales of like 100 processes or something when machines were much smaller. But in recent history, this is something that's really been lacking and necessary for some of our scientific analyses. So we made this parallel library called Tess, built on top of DIY. And it has many applications that we've demonstrated. This will be a paper in this year's SC, by the way, in SC 14. And I will here look at some performance numbers. This is strong scaling, so the size of the problem remains the same as we scale up the number of processes. We're going out to a maximum of 128,000 processes here. This is on Mira. And the dotted line is ideal 100% efficiency, right? And you can see the slope relative to that dotted line for 5 different size problems. The largest one going up to 2K cubed, so 8 billion total particles, right? Scaling out to 128,000 processes. Some of the larger data sets in strong scaling scaled out to about 90% strong scaling. It's very good. That's end-to-end scalability. And the horizontal lines here are an indication of weak scaling, where the problem size does grow as the number of processes grows. So if we go and double, or I should say, if we go to 8 times larger the total number of particles, and then 8 times higher process count, that will basically connect us on points on these horizontal lines. And end-to-end, that's about, I think, 98% weak scaling. So both strong scaling and weak scaling are very good for this problem. Now, we cheated a little bit here. These are synthetically generated particles that are nicely load balanced. Okay, as these things in a real simulation become more clustered and more irregular, the scalability obviously drops down more to like 50% is what we see in real applications. Okay, but that still isn't too bad. And then just for some actual uses of this in cosmology, one of the fields that we work in quite a lot, we take this tessellation, we can segment it, we can do connected component analysis on it, we can threshold it and break it out into connected components. We can analyze the statistics of the volumes of the cells. If we do that over time, from early time steps to later time steps, we see the distribution of the cell volume become more pointed, more skewed to the left. This exactly matches large-scale structure formation in the universe, basically the clustering of dark matter particles into halos and the spreading out of them in other regions into voids. These basically, in modern day, become places where galaxies live, right, in these clusters. So this exactly matches the physics. And then, as I showed you at the beginning, kind of this larger data flow or workflow of successive analysis operations, another analysis operation that we can do if we start with raw particles and go through the tessellation to a regular grid density estimate. So that is now, I want to, onto a regular grid, figure out the density at each grid point of this original discrete particle distribution. Turns out that's more accurate if we go through the Voronoi tessellation as an intermediate representation. And so that's what we've done. And so we can now hook a couple of these analyses together. And both of these are actually DIY parallel programs running at scale now. So with that, just to summarize and get us sort of back on track, we talked about the block abstraction instead of tasks as kind of the unit of decomposition and the unit of work, right? As a natural data-intensive kind of way of thinking about data as a first-class citizen, right? Now, if we take those data operations and push them into a separate library that is reusable, that's another fundamental idea that we discussed, right? Then we looked at usage of that library in terms of design patterns, those flow charts, right? And we looked at patterns that showed execution in a single core and in a separate core, static and time-varying patterns, and different communication patterns like global reductions and nearest neighbor communications. And all of that to the benefit of, being more systematic about our data analysis, right? Being independent of underlying implementations, right? abstracting away high-level ideas that can be reused, hopefully more productive in terms of our time as programmers, right? Standardizing kind of the space, right? Helping to think about these different patterns in a systematic way, right? Being able to benchmark their performance as well, right? All of these things come from kind of thinking about analysis in this more structured DIY approach. The two papers at the top are about DIY itself, and the rest of the papers at the bottom are about these applications, these libraries on top of DIY, Tess, OSU Flow, ITL, Morse Mail Complex, and so forth. And DIY can be found here. And we thank the facilities and our funding sources, and I'm happy to take any questions that you have. Oh, absolutely. Yeah, so the cosmology applications at full scale, the hero runs are about 1 trillion particles. Exactly. So these are still a subset of that. Yeah, yeah, absolutely. We have real needs for these kinds of scales. Yeah, they're not just stunts. Yeah. Other questions?
Where you used the Morse tessellation to improve the regridding, how did that help?
We compared that to, in particular, to cloud and cell density estimation. And it's much more accurate when the data, when you get into sparse regions where you don't have enough samples, when you don't have enough particles. Because having a continuous field means that you can interpolate throughout it, right? You basically have a density that you can compute everywhere, right? Whereas if you just have the discrete particles, even if you do cloud and cell or nearest grid point, if you don't have enough particles there, you're kind of toast. You get 0, right? So you get a bunch of noise in the sparse regions that we can avoid. And we have systematic comparisons of that we're trying to publish.